Okay, so we have looked at the register bank side of things in some detail in terms of how we would break up a computation into steps. Now let's look a little bit deeper into what the arithmetic and logic unit looks like, right? So let's take a look at the kind of ALU that would be required for our specific case, right, which is the discriminant computation. And we are going to assume that we have an arithmetic unit that can perform 4 types of operations. It can add, it can subtract, it can multiply, and we will also assume that it can divide. Now technically, as far as the discriminant computation is concerned, neither the add nor the divide are required, but that's okay. We want to have a solution that could be used for other things in future as well. Now I also need to decide on my number representation, and in this case I am arbitrarily going to choose that each of the inputs to my arithmetic module is 8 bits in size, right? And I am also going to make the assumption that the output therefore is also 8 bits. Now there are obviously a number of problems that you can imagine here. 8 bits is not a very big number representation, which means that it's very easy to imagine that you might end up with numerical overflow, right? You just add a few numbers and you suddenly find that the number goes out of the range of what can be represented in 8 bits. You might have carry, which is essentially similar to the overflow, right? You might have essentially either the carry or the borrow if it's addition or subtraction, which causes some kind of a error, not an error, but at least a condition that cannot, where the result cannot be represented within the number of bits that you have. Now even more serious is, for example, multiplication, because it's even easier for multiplication to overflow out of the 8 bits that we have. And as far as division is concerned, it's very likely that depending on how we have gone about implementing division and how we interpret the numbers, we might actually end up with either many of the results basically becoming 0, right? You are just doing integer division and the result becomes 0. How do you, for example, represent fractional numbers? Well, right now we can't, right? So all of that is sort of just swept under the carpet for now, but hopefully it's clear to you that these are not major problems. All I need to do is change my number representation, and nothing else that we discuss over here actually changes, right? Now the good part about these kind of simplifying assumptions is that I can make certain similar simplifying assumptions for how my hardware is actually built. If you are actually trying to do, let's say, 32 cross 32 multiplication, right, or a division that requires some kind of fixed point representation of the result, it may turn out that even doing these kind of things in a combinational circuit, or in fact even just doing division in a combinational circuit, may not be very straightforward, right? So right now we are just brushing all that aside, right, saying that okay, these are problems that can be solved. The fact is, even if you need a more complicated circuit which involves, let's say, a finite state machine in order to do the data path and control in order to actually do the computation, that can ultimately be brought within the same sort of purview of what we are trying to do here, right? So okay, so far so good. We have 2 inputs, we have 1 output, and we would also want to be able to select out of these 4 operations, right? Now given that we have 4 operations, it means that the number of bits that we require for selection is basically 2 bits, right? If we had even 5 operations, then we would need sufficient number of bits to encode all the values 0, 1, 2, 3 and 4, right, because we need unique representations for each of the operations, which basically means that we need at least 3 bits. So therefore, if I have n operations in general, what I would need is log n to base 2, the ceiling of that, right, if it's not an integer, that many number of bits for the selection. This is exactly like if you have a multiplexer and you need to sort of select between multiple choices, how many bits of selection do you need, right? Now let's look at what the Verilog code for something like this would look like, right? And it turns out that we are actually precisely implementing a multiplexer, right? What we have is 2 inputs A, B that are of this parametrized width, and the result is also of the same number of bits, and the operation over here is parameterized. Well, it's not parameterized, it's just hard coded as a 2-bit operation in this case, right? Now once again I am using sort of good practice design in Verilog, and I go ahead and say that let the operations be explicitly defined as 0, 0, 0, 1, 1, 0, 1, 1, right? You might wonder why not use an enumerated data type over here. You could, but you have to be a little more careful over here, because this operation code is actually coming in from another module. So you need to ensure that if at all you define an enumerated data type out here and you want to use it, that enumerated data type should be common across this module and the other one that you have. You cannot, for example, afford to have a scenario where for whatever reason the compiler decides that the enumerated data type in one module should be enumerated starting from, let's say, 3, and in the other one it should be enumerated starting from 0. Now typically the compiler will not do that, right? They normally follow fairly standard practices. But the point of an enumerated data type is also that you don't really focus on what the actual enumerations are. You only care about the order. Now, in our case, since we explicitly want to know what the operation codes are in each case, a local param is probably the best way of coding it, right? So I'm using this encoding that the addition operation is encoded as 0, 0, subtraction is 0, 1, multiplication is 1, 0, and division is 1, 1, right? And now let's look at what our logic looks like. It's actually very straightforward. It just turns out to be a case statement in Verilog, right? And what it says is, if the operation is add, then result is a plus b. If it's subtract, it's a minus b. If it's multiply, it's a star b. And if it's divide, it's a by b. Now this is a little tricky, right, in principle, because it's not clear what this synthesizes to, for example, right? And there are many scenarios where if you actually write code like this and try to synthesize it, most likely the Verilog compiler will fail, right, saying that it doesn't know how to implement a divider in a combinational manner, right, because after all I have specified that I want it to be combinational. Multiplication can actually be handled. Most compilers are smart enough to figure this out, right, and most compilers also have built-in sort of modules that allow them to implement multipliers in a fairly efficient manner. Division is a slightly more complicated task. Combinational circuit for division is actually pretty unlikely that you will come across one, right. So what that means is, right now the way this code is written is something that will simulate fine, but most likely may fail to synthesize. So if you think about it, how would you get around this? Well, one way to do it, assuming that you have some way of implementing a combinational division, right? If it's not combinational and takes multiple cycles, that's something we'll need to get to later, right? We can't really talk about it right now, but we will definitely be looking at what happens if you have more complicated instructions later. But assuming that I had some kind of combinational circuit that can perform this, all I would need to do would basically be to come up with something like, maybe instantiate a divider, right, which would take a, b, and would give some kind of output, right, and instead of this I would basically give the value the value out, right. So what does that mean? It means that this divider is actually permanently fed in with the values a and b, and every time it's basically computing the value out. And all that is happening over here is, if the operation happened to be opdiv, I actually select that out and feed it as the actual result of my circuit, right. So technically what is happening out here, if you think about it, is I have this circuit, right, which looks like a black box. It has two inputs, a and b. Now internally there is an adder that takes a and b as inputs. There is a subtractor, right, and I need to be able to perform subtraction separately, right, which again takes a and b as inputs. There is a multiplier, right, once again takes a and b as input, and there is something that does division that once again takes a and b as input. And what this case statement over here does is, well, it multiplexes between these results, right. So all I have over here is my 2-bit operation is being used as a select in order to decide what my result looks like. Now as you can see, this is essentially a completely combinational circuit, right. What I have over here is a path from input to output where there are no registers, at least assuming that I know how to implement division also without needing a register. It just sort of, you give it an input, and after a certain amount of time, some number of nanoseconds presumably, the result appears out here, right. What are the input to output paths as far as the circuit is concerned? I have a path from A, that is all the 8 bits of A, right. I need them to sort of stabilize, and after that there is a path that sort of goes through the plus, it goes through the multiplexer and finally comes out to the result. Similarly, there is from B through the plus, through the multiplexer and out to the result. A through the subtractor, A through the multiplier, A through the divider, right. Now it's not just that, there is also a path that goes from the operation select through the multiplexer and out here, right. So what we have is some kind of a circuit with like multiple different paths leading from the various inputs going through to the output. And as we have seen, what we are finally concerned with in that case is which is the longest among all of those paths. Now intuitively, by looking at this, you might imagine that this particular path which just goes through op, right, and through the multiplexer and comes out is probably not a whole lot of delay on its own, right. If I assume that the rest of the inputs are already ready and unchanging, what I am asking is if this input alone changes, how long could it potentially take for the data to ripple through and come through to the output? That's just pretty much the delay of a multiplexer. As far as an adder is concerned, it would be the delay through the ripple carry adder and also presumably the delay through actually the gates that constitute the multiplexer, right. So it becomes more. So even if the multiplexer by itself, the input select bits are not changing, that doesn't matter, because as long as these inputs change, the multiplexer needs to perform some kind of logic computation in order to get the output over here. So the delay becomes the delay through the adder and through the multiplexer. Subtractor is presumably very similar to an adder, but a multiplier is almost certainly a significantly larger delay than an adder. So what we have is it goes through the multiplier, right, goes through this and finally comes out on the result over here. So what that means is that we are interested in finding what is the longest combinational path through this circuit, right. For now we are not going to talk more about it, but eventually we will see that this is actually a very crucial part of the operation of this entire system, right, and it sort of determines how fast our processor can run. So right now as things stand, we have a purely combinational arithmetic unit, right. In general we call it an ALU or an arithmetic and logic unit, because very often certain kinds of logical operations, what I mean by logical operations are things like shifting, right, shift left, shift right, and certain kinds of comparisons, or certain kinds of actual Boolean logic operations like AND, OR, XOR, or even just NOT, which is inverting a set of bits. All of those are usually performed in the ALU, right. Anyway, the good thing is this ALU is purely combinational, at least as things stand right now. It's very easy to add more operations. So if I wanted, for example, to bring in the logical operations AND, OR, XOR, NOT, it would just mean that the number of operations has gone from 4 to 8. I would need at least 3 bits out here and I'm set. I just have to expand the number of entries in my case statement. I've also parameterized the operand width, which is a nice touch. It basically makes it easy for me to scale this and just change and experiment with parameters as needed. More importantly, it's just good design practice. Now we also have a register file, right? And what does the register file look like? In this case, remember that we are talking about something where we want to be able to read 2 inputs because we need 2 operands for the ALU, and we want to be able to write 1 value, right. So we want 2 read ports, we are going to call them RS1 and RS2, and I want 1 write port. Now in addition to that, I also need to decide how many registers I want to work with. The example that I showed for the register bank had only 4 registers. But if you think about it, I already have A, B and C as my 3 input parameters. I have the number 4 which I will probably need for some computation and needs to be stored somewhere. I then need to perform temp1, temp2, temp3 and result, right. So it looks as though trying to sort of get everything done with just 4 registers, it may be possible, but it's not going to be easy, right. So let's not skimp on registers here, let's just go for 8 registers in this case. What that means is each register address is now 3 bits because I need to select a value between 0 to 7. So this is what my register file module interface now looks like, right. It has a clock, right. Why does it have a clock? Well, because I need to be able to write values back into the register. Registers are storage units, they are clocked. I also have a write enable. Without that I can't control when I actually write into the register. But then what I have is 3 bits of RS1, RS2 and RD, right. I don't actually need to have like multiple values coming out. I only need to provide the addresses of the values that I want over here. Now you can probably see that there's nothing in the logic as such preventing me from having RS1 equal to RS2, for example, or for that matter even being equal to RD. Right? What that would mean is both the multiplexers for the reading are essentially reading from the same source register, which is perfectly fine. They are also writing back into the same register, and all that means is that the write operation anyway happens at the next clock edge, right? So it doesn't interfere with whatever value I read out now. So the value that I read out now and the value that I write back at the end of the clock cycle could very well be different. So these three are the ones that determine which registers are being used. The write data determines the actual value to be written, and RS1 data and RS2 data are the actual outputs. Now these values are the ones that are used to interface with the ALU. Right? As far as the ALU is concerned, it only cares about what RS1 and RS2 data are. It doesn't care about the addresses, it doesn't care about the destination address, it provides the write data, right? And that in turn needs to be fed into the ALU provides the write data, which needs to be fed into this write data port of my register file. So let's start putting everything together, right? We have a certain data flow out here, right, which we can try to sort of draw out, right? I have a clock and presumably there is some data stored over here, right? So I have RS1 data and I also have RS2 data, right? Now where did these come from? Basically from the addresses, right? The RS underscore addresses, RS1 and RS2 addresses. What happens with this is these values go into an ALU, which is a combinational logic unit, and this in turn goes into another register, which is basically the the write data, right? And this part of it basically sees the RD address. Now you might wonder, why do I have two registers out here, one over here and one over here? Well, it's actually just that these are two parts of the same thing. I've just drawn them logically different. What actually happens in practice is that this sort of goes back over here and connects back to the input, right? I've just sort of drawn this input side out here for easier sort of visualization of what the data flow that is going through this circuit looks like. Alright, so far so good. It basically looks like we have a very regular kind of data path out here, right? Something which basically starts off with data coming out of a set of registers, going through an ALU and finally feeding back into a set of registers along with appropriate control signals. Which leads us to the question, what about the control? Where is that coming from, right? Who is determining this source addresses, the destination address, and well, the operation selection for the ALU, right? All of these are things that are control signals, right? And as we have already seen, this is essentially our data path. We need some logic that generates a set of control signals for us. So let's look at how we would instantiate this, right? Our ALU reg file combination, right? I'm just giving it a name ALU reg file top because it's not yet the top level of our processor, right? We are sort of building towards a processor at this point, but we are not yet at the top level. We are not completed the story. So the ALU reg file, the top level, it takes a clock as input. It also takes a write enable as input, which sort of allows us to control when we are updating the registers. It takes the ALU op as input, right? And where is this ALU op coming from? That's something that we'll need to think about and solve. That problem has to be solved. It also assumes that RS1, RS2 and RD addresses are all given as inputs. The output of this is basically the RS1 data, the RS2 data and the final result, okay? Now if you look at it, right, actually speaking, RS1 data and RS2 data probably do not need to go as outputs of this module, right? So you could say that I don't really want these two values to be outputs. I don't want this to be an output either, right? These values do need to be inputs because I don't really have them coming in from anywhere else. I could choose this, but it would primarily be if I wanted to do some kind of debugging. strictly speaking, all that happens over here is RS1 data gets connected to the RS1 data out here, RS2 data gets connected to the RS2 data out here, and the result gets connected to the result out here, right. So, this sort of forms the closed loop that we have over here. The operation, the write enabled signal as required, as well as all the addresses that I am concerned with are actual inputs that come in from outside, right. So, these blocks essentially sort of sit inside the module that we have out here. So, now let us look at how we might go about constructing a piece of code that would actually tell us how to go about using the ALU systematically the way that we want, right. So, I am going to make certain assumptions out here, right. First of all, as we already assumed, B, A, C, all of those are 8-bit values. I am also going to assume there is no problem with overflow. So, for example, if B for example had the value 100, which is a valid 8-bit value, then B squared is actually well out of the range of what can be represented in 8 bits. I am not concerned about that. That's not a problem I am interested in solving right now, right. You could either choose to go with like more bits, maybe 32 bits, or you might say that your numbers have to be small enough that such a scenario can never arise, right. So, once we have sort of pushed that aside, right, I am making certain assumptions out here that R0 contains the value A that I want to work with, R1 contains the value B, R2 contains the value C, okay. Now, how do I get the values A, B and C into R0, R1 and R2? That's left for another time, right. I don't have an answer for that right now. We will of course be answering that question, but not right away. For now, just assume that somehow I managed to get A, B and C into R0, R1 and R2. Now, I also need to have this value 4, and that's where you realize that the way that we have constructed the ALU right now, it assumes that the source values RS1 data and RS2 data are both coming from the register file, right. I don't have a way of directly giving it a constant value 4 as an input, right. So, what do I do? I am going to simplify things for now and just say, okay, R7 contains the numerical value 4, right. It's essentially the equivalent of what's called an immediate operand, right, in the context of assembly language coding, right. And this is not necessarily the only way of handling it. Putting the value into a register and using it from the register is of course one valid solution, but there are simpler solutions. You might be able to encode the immediate operand directly into the instruction itself. Well, I am sort of jumping ahead here. We still don't know what an instruction is, but there may be some way by which we can sort of get to that, right. So, again, how do I load the value 4 into the register is left aside for now. So, well, why did I choose R7? It was just a number, right. I could have picked R3, but I have already run out R0, R1, R2, R3, so I am out of the first 4 registers. I know that I need more registers for my other computations, so I just chose R7 to hold the constant value. And of course, this now raises the question, how many registers do we need, right? Clearly, we need more than 4 if we want to perform a computation like this, right? So, we are going to go through and sort of break up and say, let's look at the steps before we decide on the final number of registers. So, the steps that I am going to perform, I know that R1 contains the value B. So, my first step is going to be, let's take R1 into R1, right, and store the result somewhere. I can't store it in R0, well, because that still contains the value A. Could I store it in R1? Possibly, yes, right. I mean, because after all, once I am done with this B squared, I don't really need the value of B again, except that if I look at the overall solution to the quadratic equation, I do need B somewhere else. So, let's not overwrite it for now. I am just going to put the value in R3, okay. And I need to perform A into C, A is in R0, C is in R2, take the result and put it into R4. Again, could I have chosen to overwrite either R0 or R2? Potentially, right. The point is that answering this question of do I need this particular value again in future, right, turns out to be not a very trivial problem to solve. You actually need to define something called the lifetime of a variable, right, which sort of analyzes the entire program and says, okay, is this particular variable ever going to be used somewhere else again? And if it turns out that the answer is no, then you could go ahead and overwrite it with something else. For now, we are not getting into all of that, right? So in this particular case, for example, if you look carefully through your instructions for the entire quadratic equation, you will probably see that after this a into c has been computed, I never use c again by itself, but I do use a, right? So writing into R0 is probably not a good idea, but maybe writing into R2 would have been fine, right? Right now, once again, I'm just sort of brushing the problem aside and saying, okay, I have more registers, right? I'm going to use R4 instead. Now, in this case though, right, I'm just taking AC and multiplying it by 4. It's very clear I'm not going to do anything else with it. So, why use R5 out here? I'm just going to do R4 takes the value R4 times R7. This also illustrates a sort of nice feature out here. The fact that I am using R4 as one of my inputs and also one of my outputs. So it's both a source register and the destination register. But as we just saw by looking at the path through the logic, right, there is no conflict over here, right? The readout of the register happens at the beginning of the clock cycle. It then passes through the combinational logic, and at the end of that clock cycle, just before the next clock edge arrives, I need to make sure that my setup time at the input to the register file is satisfied, and sure enough R4 will get updated with the new value, which in turn will be ready to be read out from the register file in the next clock cycle if you need it. Okay. And in this case it happens that we do need it, right, because in the very next instruction I am using R4 as R3 minus R4 and I am storing the result in R5. Once again, could I have chosen to overwrite one of these? I am leaving that problem aside. So now what it looks like is I had R0, R1 and R2 as storing my inputs, R7 storing a constant value which is once again an input, and R3, R4 and R5 being used for the computations. The net result is that the final result of my discriminant computation lands in R5. Now why R5? Because I wrote the instructions that way, right? Could I have done it differently? Of course I could have. I could have chosen to put the result in some other location instead. And it turns out that there are actually some conventions that are usually followed, but those are conventions primarily in software, right? So the C programming language, for example, follows something called the C ABI, the application binary interface, which says that for simple functions, the final result, especially if it's an integer type, should come into a certain register, and that register will automatically be available to the calling function, right, where it can sort of observe and say, okay, this was the return value of this particular function. Now if you are returning something more complicated than an int or something that fits within a single register, this doesn't work. So then you need some other kinds of return conventions, return value conventions. But right now we don't care, right? From the hardware point of view, I really don't care where you store the result. As long as I can tell you where the result is, you should be able to use it to do whatever else you want with it. Okay. Now let's look a little bit at the timing of all of these signals, right? What I mean by timing is these are after all digital logic signals, right? And they are produced by some kind of circuit activity. Now what actually happens in practice over here is that there is some clock edge which is sort of off the left hand side of my chart out here, after which there is some kind of logic that finally leads to this particular R1 signal getting the value of the first RS, or rather the RS1 address getting this value R1 or 001 in this case, right, which basically says read from register R1. Similarly, in more or less the same time, right, because I can assume that it's the same kind of logic used in both of those cases, RS2 address also gets the value R1. Similarly, the ALU operation will get a code, the 10 code, which we decided on, corresponding to the operation multiply. There is also something that has to determine the write enable signal. In this case, I'm going to say write enable is required because I do need to write my result back into some register, right? And which register do I need to write into? That is R3, and that is specified in the RD address. So all of this logic is something that was determined at some other point in time, right, by some means which we have not yet specified. and needs to get sort of decoded or unpacked into these codes 001 out here, 001 out here, 10 out here, and 011 out here, right. These are the codes corresponding to the different values that I want to use. Now, after I have done all of these and given these values, this actually goes through the ALU, right. Well, it actually goes through the reg file to read out a value and then through the ALU, and the final result b squared is computed from the ALU, okay. And all that really matters to me is at the next positive edge of the clock, right, and some setup time before that, I need to ensure that this value b is stable, or rather b squared is stable, right. So, there is clearly some amount of dead time required for this computation, right, which is basically when the gates inside the multiplier are sort of toggling back and forth, right, switching back and forth, but they have stabilized at this point, and that point is, well, the way that I have drawn it, well before the setup constraint required for this particular clock edge. And as long as that is the case, yes, b squared will get properly written into the register, which register R3, because the write enable signal was high at the clock edge. Okay. So, this is sort of the relative timing of the different signals as they pass through the logic that we have. So, a few key points to keep in mind over here. ALU operations, the way that we are designing it right now, should be purely combinational. Now, well, every rule has exceptions. For the time being, I am just going to leave it at that, right. Having non-combinational ALU operations is definitely something that you can handle while building a processor. Without that, you will find it hard to build a non-trivial processor. But right now we are going to leave that aside, right, because we want to sort of focus on how the basic processor looks and how we can do certain analysis like the critical path and the operating frequency and so on. And after we have done that, we will see, okay, what happens if I have an operation that cannot be performed in a single clock cycle, right. Yes, it can be handled. It complicates your control logic and so on a little bit, but well, there are ways of getting around that. Okay. The register file in our case provides storage and basically data routing, right. What I mean by data routing is it allows you to sort of take, let's say, something like R3, which is R1 into R1, and then route it to the next operation, which is the R5 update. Okay. So, it sort of acts as a temporary storage, as we saw when we called them temporary variables, right, and allows us to take a value that has been computed in one place and forwarded appropriately to another place where it can perform another kind of computation, right. So, this kind of timing is basically critical. The timing that we have, right, which we saw in this chart out here, is critical for correct operations. We basically have a sort of register decode which decides what are the RS1 address, RS2 address, ALU op and so on. We also have the actual ALU operation itself, right, and rather the register decode and reading out. So, the multiplexing that happens at the output of the register and the ALU operation together form a critical path. And each of these operations basically requires multiple control signals. Okay. So, when we take all of these things into consideration, it suggests that, look, if I look closely at what is happening out here, right, each of these things, specifying a register, specifying the ALU operation, deciding where the result needs to be sent and so on, can all be sort of represented using a few bits, right. Can I put all of those bits together and create some kind of a code, right, that tells me that this particular operation needs to be performed on these inputs at this point in time. That essentially is what we call or refer to, right, by the name instruction encoding, and that is what we are going to look at next.